Good morning, everybody. Happy Monday. It is Monday, December 18th. Golly gee, Christmas is just a week away. I have so many preparations to do. I gotta write the list, check it twice, make sure the reindeer are all in order, sort the magical dust. There's a lot to do. Gotta get gifts, you know? Holy moly. Also have a bunch more calculus to do. But hey, it's only 7 days now. If you haven't seen all the other episodes, all the other hours of calculus that I've done for you, check it out, okay? There's a link to the playlist in the description. I'm going to look for the 18th box, the 18th chocolate compartment in this calendar. Went to a football game yesterday. Like I said, that was a ton of fun. But I ate way too much food this weekend, which is why it's really important that I, get out of bed at midnight on Monday to come eat chocolate and do calculus. That's super important. Okay, so I'm going to get into this compartment. There's compartment number 18 right here at like the windowsill. It's very pretty. Look at those creepy bears staring at us. Oh, gosh. Ugh. I'm going to put today's question on screen while I get into this compartment. Today's problem is a Diffie-Q problem, differential equations. I'd love to make more videos on differential equations. It's a relatively small part of the AP Calculus curriculum, but it's pretty common for AP Calc exam to have one big, Diffie-Q free response question. I took differential equations. I remember I had this big textbook, real big textbook, one of my bigger textbooks, and honestly, I didn't really find the class that remarkable. It was fine. It was cool. One of those nice red soft chocolates. God, I feel like it was an eternity ago I studied differential equations. Oh my God, I'm old. Probably would have been 2017 I studied differential equations, 6 years ago. Man, those red chocolates sure do hit. All right. Let's do the calculus problem, I guess. This is free response question 4 from the 2015 AP Calc AB Exam. Let's read it. Consider the differential equation dy dx equals 2x minus y. Part A. On the axes provided, sketch a slope field for the given differential equation, this one here, at the 6 points indicated. All right, let's just create a quick table with the xy values that we are interested in, see what the derivatives are at those points, and then sketch some little tangents so that we end up with a slope field. Here's my table of xy pairs, and then in this third column, we'll put the derivative dy dx, which is just 2x minus y. At, let's see, this point here, where x is 0 and y is negative 1, 2x minus y is 0 minus negative 1, which is positive 1. At this point here, where x is 0 and y is positive 1, 2x minus y is 0 minus 1, which is negative 1. At this point 0, 2, 2x minus y is 0 minus 2, so that's negative 2. At this point here, 1, negative 1, 2x minus y is 2 minus negative 1, so 2 plus 1, so 3. At this point here, 1, 1, 2x minus y is 2 minus 1, which is 1. Finally, at this point, 1, 2, 2x minus y is 2 minus 2, which is 0. All right, now we can sketch the slope field by sketching some little tangents that capture the right idea of what's going on here. Like, for starters, the point 1, 2 right here has a derivative of 0 at that point, so we should have a horizontal tangent like that. At, let's see, let's go back to the top. So 0, negative 1, that's right here. We should have a slight upward slope because that's a positive slope of 1. So something like that. Let me try again just to make that a little more straight. Then at this point, 0, 1, we should have the same sort of slope as before, but negative. So at 0, 1, right here, we'll have a slight negative slope, something like that. At the point 0, 2, so way up here, we should have a steeper negative slope of negative 2. So something like that, perhaps. Then at 1, -1, we should have our steepest slope of all, a slope of 3, and it's positive. That's right here at 1, -1. So maybe something like that, or maybe that, just a little bit steeper. At the point 1, 1, that's our last one to sketch, we have a slight positive slope of 1, so it should be the same sort of slope as this guy here, so maybe that looks something like this. And there you go. Remember, you're not going to be able to sketch these slopes exactly, but you want to keep the general idea correct. This guy here with the slope of positive 3 should be steeper than any of the other lines, and obviously it should be going upwards. This one should be horizontal. This one here should be steeper than these others that have slopes of plus or minus 1. Just get the general details correct. Moving on then to part B. Find the second derivative of y with respect to x in terms of x and y, and then determine the concavity of all solution curves for the given differential equation in quadrant 2. So the differential equation here, we're going to be able to make a statement about the concavity of its solution curves by finding this second derivative. Also remember, in quadrant 2, x is negative, but y is positive, so we will consider that once we find this second derivative. To find the second derivative, we'll just differentiate both sides of the first derivative. This is the differential equation that we were given. Let's differentiate both sides. If we do that, then on the left, we are going to have the second derivative of y with respect to x equals, on the right, the derivative of 2x is just 2, and the derivative of y is dy dx. But of course, we know that dy dx is this, 2x minus y. So let's just replace that dy dx with 2x minus y. And then we can distribute the negative here and find that this equals, let's put the positive y first. It's going to be y minus 2x, and then plus 2. And if we want to factor out the 2, we could rewrite this as y, let's say plus 2 multiplied by 1 minus x. Then, addressing the concavity part of the question, in quadrant 2, like we said, x is negative and y is positive. So if we look at our second derivative, we know that 1 minus x is going to be 1 minus a negative in quadrant 2. Which is 1 plus a positive. So 1 minus x is obviously going to be positive in quadrant 2, and that makes it clear that this whole second derivative is going to be positive, because the only other thing in question would be y. But if we're in quadrant 2, then we know that y is positive. So we can say for sure this second derivative, y plus 2 times 1 minus x, is positive, which means that in quadrant 2, every solution curve has to be concave up. All right, moving on to part C. Let y equals f of x be the particular solution to the differential equation with the initial condition that f of 2 equals 3. Does f have a relative minimum, a relative maximum, or neither at x equals 2? And justify our answer. To determine if there's a relative minimum or a relative maximum, let's first plug x equals 2 into the derivative and see if this is a critical point. If it's not a critical point, then no further investigation is needed. If in fact this is an extreme value, the derivative should be 0, where x is equal to 2. So let's evaluate this. So for part C, we're evaluating dy dx at x equals 2. And remember, in this problem, we're told that when x equals 2, the function is equal to 3. So we could say this is at x equals 2, y equals 3. Now the derivative, dy dx, is 2x minus y. So this is 2 times x, which is 2, minus y, which is 3. This is 4 minus 3, which is positive 1, which is not equal to 0. Thus, no further investigation is necessary. F does not have a relative minimum nor a relative maximum at x equals 2 because its derivative there is not 0. So there is our conclusion. There is no extreme value at x equals 2. Moving on to part D, find the values of the constants m and b for which the line y equals mx plus b is a solution to the differential equation. Alright, well, if y equals mx plus b, what is dy dx, the derivative? Naturally, that would just be m, the slope. So we would need m to equal 2x minus y. All right, let's write this down and start doing some work. All right, again, if y equals mx plus b, its derivative is just the slope, which is m, which, if it's a solution to our differential equation, we know that this should equal 2x minus y, because that is the differential equation that it must satisfy. Now, what can we do with this? Well, we might have that m equals 2x minus y, but we also know that y equals mx plus b. So this is the same as m equals 2x minus mx minus b. We can then do some factoring to see that m must equal 2 minus m times x. That's factoring the x out of those two terms. And then, of course, minus b. Now we can use a method called equating coefficients. On the left side, we see there are no x's. The coefficient of x is 0. So 0 must equal the coefficient of x on the right side, which is 2 minus m. 0 must equal 2 minus m, which means that m must equal 2. On the other hand, there's one constant on the left, which is m, which has to equal the constants on the right, negative b. So that gives us this other equation, m equals negative b, which if we want to learn about b here, we could say that means that b equals negative m. And since we found that m equals 2, this means that b must equal negative 2. So there is one possibility for m and b in order to have a curve, or in this case a line, that satisfies the differential equation in question. That one pair of values is m equals 2 and b equals negative 2, which gives us this solution curve y equals 2x minus 2. And that completes our solution to free response question 4 from the 2015 AP Calc AB Exam. Let me know in the comments if you have any questions, and please be sure to share the AP Calculus free response question advent calendar around with any of your fellow calculus nerds if you've been enjoying the videos. I'll see you tomorrow for the next episode where we will do another calculus free response question. Thanks for watching.